Section 6.2 Linear Independence, Basis and Dimension. We already know like a little bit about everything of these. I'm just gonna add more theorems. So let's start with the first example, and you will see what they're gonna tell you. They can tell you test the set of matrices for linear independence. So how we're gonna check these matrices are linear independent? We have to assume that coefficients C1, C2, C3, and C4 equal 0. That means C1A, C2B, C3C, and C4 with the matrix D is going to be 0. Then write down everything. So it's going to be negative C1 plus 5C2, C3 is 0, C4 is negative 1, so negative C4. The first equation. The second one is going to be C1, C2 is 0, 3C3, and 0C4. So here's the second one. The third one is going to be, this one is supposed to be negative. Third one is negative 3C3 plus C2 minus 5C3 minus 7C4 equals 0. And the fourth one is going to be 3C1 plus C2 plus C3 plus 17C4 equals 0. Now, if you want to solve these four equations, it's fine to find C1, C2, C3. It's up to you, or you want to convert it as a matrix, then reduce by reduced row echelon form. So by reduction, you're going to get this matrix. That's mean C1 plus 6C4 is going to be 0. C2 plus C4 equals 0. And C3 minus 2C4 equals 0. So it's up to you which method you're going to use. The main thing we need to find is the value of C1, C2, and C3. If it's zeros, that means this is linear independent. If it's not zeros, that means this is linear dependent. So in this case, we found C1, C2, and C3. We're going to let C4 equal T. That means here is the value of C1, and here is the value of C2, and here is the value of C3. We're going to let the T equal 1. So C1, C2, and C3, and C4 is going to be equal 1. So here is the scalars C1, C2, C3, and C4. That means this is linear dependent. So we can write down negative 6 as a C1 with the first matrix minus 1 B plus 2 with the C plus 1 with the D equals 0. Let's check that. Negative 6 times negative 1 is 6. Minus 5, this is 0, minus 1. So it's going to be 1 minus 1 is going to be 0. You can check both sides is going to be equal zeros. So the set are linear independent, and then you can write down any one as a linear combination from the rest. We took D and write down as a negative 6A minus B plus 2C. So that's what we're going to type here. We're going to type here. So what I did here, I write down D as a linear combination from the rest. But when I'm plugging, I plug in B, which is this matrix. You're going to move it to the other side as a linear combination from the rest. So B equal negative 6A plus 2C plus D. So the main thing we found the scalars C1, C2, and C3, and C4. So you can write down any matrix as a linear combination from the rest. So if you look to the second one, consider the following C1, C2, C3 are constant. So they give you a hint here. Here is everything. They set up everything here. And they're telling you, go ahead, find C1, C2, and C3. And then you're going to say it's a independent or dependent. That's the only thing you're going to do. So for the second example, if you look here, C1, it's already given. So now it's going to be 3C1 plus a 3C2 plus a 3C3 is going to be equal 0. And C1, there is no C2 here, minus C3 is going to be equal 0. And C2, because the squared here is 0, so C2 plus C3 equals 0. That means C1 is going to be equal C3 and C2 equals negative C3. Plug in these two in the first equations, you're going to get 3C3 equals 0. That means C3 equals 0. In this case, C1 equals 0 and C2 equals 0. That means C1 equals C2 equals C3 and equals 0. So that means this is linear independent. So that's the only thing you're going to prove here. Don't think it's hard. So that means you're just going to type C1 is 0, C2 is 0, and C3 is 0. And here you're going to type independent. I think you have to type it capital. I'm not sure. Here we go. Number 3, it's exactly the same way. We need to find the constant C1 or the scalar C1, C2, and C3, and C4. Now we have 4 scalars. So if you look to this one, number 3, start this here, 1 minus 3x, and 9x plus x squared minus x cubed, C3, 1 plus a 3, and C4, 9, 3x, 9x cubed. Okay. So now we're going to do the same thing. That means C1, there's no C2 here, C3, and 9C4 is going to be 0. This is the first one. The second one is going to be negative 3C1 plus 9C2 plus, there's no C3 with the X, plus 3C4 is going to be 0. The third one, this is 0, C2, and here is C3, there is no C4. And the last one is going to be this one. So if you check here, you can solve these equations, but what I did, I convert this one to a matrix, 1, 0, 1, 9, negative 3, 9, 0, 3, 0, 1, 1, 0, and 0, negative 1, 0, 9. By reduction, reduced row echelon form. So we're going to get this matrix. That means C1 equals C2 equals C3 and equals C4, which is 0. That means this is linear independent. So the same thing now with example 3, we got all the scalars zeros, and this one it's mean independent. Dependent. That's it for the third one. There is something wrong with the word. So number 3 is right. Let's move to number 4. Number 4, they say consider the following. Now here's the difference. V, all the matrices with dimension 2 times 2. B is the matrix here. They tell you complete the following. The element of B is linearly independent. So that's the first thing we have to check. You have to check the B is a linear independent. So do exactly the same thing what we did on the first example. You're gonna get C1 with this matrix, C2 with the second matrix, and C3 with the third matrix equals 0. And then you have to find C1, C2, C3. So for this example, yes, it's going to be linear independent. The second part we need to find, so I'm going to choose here, are linearly independent. The set B has element, how many elements in the set B? So check the set B. 1, 2, 3. That means 3 matrices, because it's all the matrices. So first element, the second one, and the third one. So 3 elements. That means we're going to put the dimension for this one, 3. And the dimension for all matrices, 2 times 2 is going to be 4. The dimension for them B, which is all matrices with 2 times 2, so it's going to be 4. So let's check here. Dimension of B equal 4, dimension of B equal 3. The dimension of B less than the dimension of V. There's a theorem. I'm going to show you the theorem. In this case, B can't span V. Let's check the theorem. So the theorem for this one, 6.8, here's the theorem. We're going to check the last part. Any set of fewer than n vectors in V cannot span V. So any set, you see the set B is less than the set V. That means, therefore, the set B cannot span V. In this case, B is not a base for V. Because to satisfy the base, we have to satisfy 2 conditions. The first condition is B is a linear independent. The second one is B spans the V. But by this theorem, we find out the first condition, yes, B is a linear independent. But the second condition, V cannot span, B cannot span V. That's why, because the dimension of V is 4, dimension of V is a 3, and the dimension of B less than dimension of V, then by this theorem, B cannot span V. So B is not basis for V. That's it for this example. So let's do the same thing with number 5. I did number 5 in details. So again, we need to prove that if you look the set V equal all the matrices 2 times 2 and B equal 4 terms, these are the matrices. Then what I'm going to do, I'm going to prove that B is a linear independent. So C1, the first matrix, C2, the second one, C3, the third one, and C4, the fourth one. And then you're going to find these 4 equations, C1 plus C3 plus C4 equals 0, C2 minus C3 plus C4 equals 0, and keep going. Then if you want to solve these, that's fine. But the easiest is to convert to the matrix and then do the reduction. You're going to get these. This is the identity matrix. That means C1, C2, C3, C4 equals zeros. So now it's a linear independent. So the second thing, we need to find B span V. This is easier by using this theorem. Dimension over V is 4. Dimension over B equal 4 because 1, 2, 3, 4. This is the dimension, not the elements here inside each matrix, because B contains all these matrices. So the dimension equal 4. So by theorem, we have the dimension equal the dimension over B. So B span V. In this case, then B is a base for V. So this is, for this example, is going to be a base. That's mean we're going to choose here our linear independent and has 4 elements, and dimension of the matrices of V, which is also 4. So this one is going to be a base for V. This is number 5. So number 6 is exactly like number 5. Let's move to example 7. Example 7, determine whether the set B is a base for the vector V. Now we need to check this one as a base. So first of all, you have to check this one as a linear independent. Then you're gonna check, is B a base for V? That's what we need to check. So V is all polynomials with degree 2. Here is the base, which is 1 plus 5 plus 5x plus 7x squared. B is a linear independent. Let's check that. C1 with the first vector, with the first element here in B, plus C2 with the second one. So be careful, this is only one part, because this is a polynomial and this is also polynomial. Now it's going to be C1 plus C2 equals 0, and C1 now it's 0, 5C1, 5C2 equals 0, and 7C2 equals 0. That means C2 equals 0. Plugging in the first one, you're going to get C1 equals 0. So that means this is linear independent. The second step, dimension of V equal. Here is the important thing. Polynomial. Polynomial of degree 2, that's how it looks like. So how many terms? 1, 2, 3. That means dimension of polynomial with degree 2 equal to 3. Dimension of B, which is 1, 2. So 2. That means dimension over B less than dimension over V. By this theorem, B is not a span over V, so B is not a basis for V. So that's the important thing here. Dimension of the polynomial with degree 2 is 3. So we're just gonna say it's not a base for V. For number 8, we're gonna do the same thing. We have B, all the polynomials with degree 2, B equal 1 and 1 plus 5x plus 6x squared. So let's check this one. The first thing, we need to find the element of set B is linear independent. You're gonna check that, yes or no. So the first thing we need to check, B is a linear independent. You can do exactly the same thing like this example, how to check it's linear independent or no. And I think this one, yes, it's a linear dependent. Check that. The second part is B span V. The dimension of B is 1, 2. The dimension of V, again, it's a polynomial with degree 2. So here's the general form. So the dimension for this polynomial is going to be 3. That means 3. So dimension of it B less than dimension of it V. In this case, by theorem 6.8, B is not a span V. So B is not a base for V. So we're just gonna choose is not. First of all, dimension of B is 2. And for all polynomials with degree 2 is going to be 3. And that means this is not a base for V. That's it for number 8. Number 9, they ask you to find the coordinate vector of A with respect to the base. That means the coordinate vector is the scalar. So when you write down A as a linear combination of the base B or the base, because they're telling you here it's a base to the base B. When you write down A as a linear combination to the base, the scalar C1, C2, C3, and C4, this is going to be the coordinate vector. So let's check number 9. So we have A And here's the base B, C1, the first matrix, C2, the second one, C3, the third one, and C4, the fourth one, equal A. So here is the matrix A. Now it's going to be C1 plus C2 plus C3 plus C4 plus equal 1. There is no C1 here because all zeros. C2, C3, C4 equal 2. And keep going until you got C4 equal 4. Then by back substitution, you're going to get C3 equal -1, C2 equal -1, and also C1 is going to be equal -1. So we have C1 equal -1, C2 equal -1, C3 equal -1, and C4 equal 4. So this is the coordinate vector. And if you want to check that, go ahead and plug in C1 here, C2, C3, and C4. This side is supposed to be equal to matrix A. That's when you need to check. So this one is called the coordinate vector. So we're going to type here -1, -1, -1, and here is going to be 4 for this matrix. That's it for number 9. So for number 10, they're telling you extend 7 plus x and 7 plus x squared. This is a base. We need to extend this base to a base for all polynomial with degree 2. So what we're going to do, we're going to add the standard base for the polynomials, which is 1, x, and x squared. So we need to add this one, the standard base. And then we're going to check. The standard base for polynomial with degree 2 is 3, because a plus bx plus cx squared. So the dimension for the polynomial with degree 2 is 3. So now I need to get a base when I extend this base to a base with degree with 3 terms. I have now 1, 2, 3, 4, 5. So let's check the first one. If I took the first part here and write down as a linear combination with the second, with the last part. So 7 plus x squared. When you add these together, it's going to be this term. That means I don't need this part. So I'm going to cancel it. I'm going to cancel the x squared. The left here, the new base is going to be 7 plus x, 7 plus x squared, 1, and x. Now let's check again. If I took this one, I can write down as a 7 plus x. That means x already exists here, so I don't need the x again. So I'm going to cancel the x. That means our base is going to be 7 plus x, 7 plus x squared, and 1. So 1, 2, and 3. Now the dimension for this base b, let's say b equal 3. So we extend this base to a base with a 3, with dimension 3, which is going to be base for all polynomial with degree 2. So we got it right. That's it for example or questions 10.